Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone. In this video, I will explain the concept of boundary condition in electrostatic. So far, we only consider existence of electric field component, which is electric field intensity and electric flux density, exist in a single medium. So, but what happens if an electric field travel from one medium to another? So, which is from, for example, from conductor to the dielectric, for example. So, conductor to conductor, dielectric to dielectric, which is that particular medium has different value of electric permittivity. Alright, to understand that topic, so let's consider this figure. So we have two medium, which is medium 1, which is having value of electric permittivity is equal to epsilon 1, and a medium 2, which is having electric permittivity is equal to epsilon 2. So the electric field intensity is travel from medium 2 until medium 1. So inside this medium 2, so the electric field intensity is represented by this vector, so vector E2. So when this vector travel from medium 2 to the medium 1, so inside the medium 1, the electric field intensity is represented by this vector, which is a vector E1. So those vector can be divided into two different components, which is the normal and tangential component. So therefore, for vector of E1, for example, is equal to vector of Ein. So this one is a normal component for this vector plus vector of E1t. So this one is tangential component for this vector. Same goes to the vector of E2, can be divided into two different components, which is normal and a tangential component, whereas the vector of E2 is equal to vector of E2n. So this one is the normal component for this vector, so plus vector of E2t. So this one is a tangential component for this vector. Alright, in order to observe, so what is the effect of E2 and the vector of E1 when this vector is travel from medium 2 to the medium 1. So let's consider the Maxwell equation as shown in this figure. So we have closed integration of line of vector of E dot dl is equal to 0. So this one is Maxwell equation that represent electrostatic. So in order to solve this equation, so let's consider a closed path A, B, C, D as shown in this figure. So this closed path has length of from A to B and a C to D is equal to delta L. So the unit vector that represent the distance between A, B is equal to L1 cap, and the unit vector that represent the distance between C and D given by this L2 cap. So the length between AD and BC is equal to delta H, whereas we assume that the length of this line AD and BC that inside medium 1 and medium 2 is equal between each other, which is equal to delta H divided by 2. Alright, so in order to apply this equation to this closed path line, so we can derive like this one. So whereas we have a closed integration line of vector E dot dl is equal to, so first we consider this line, so A until B. So we have integration of a until b e dot dl, alright, plus integration of b until c e dot dl. So in this case is for this line. So plus integration from c to d, so vector of e dot dl. So in this case is represented by this line, and the last part is plus integration of from d to a vector e dot dl. So in this expression is represent line integration for this part. So the solution for this integration, so we can see that, so from line a to b, so the distance from a to b is equal to delta L. So we will have delta L here, but because of the direction of this vector and the direction for this tangential component for this vector of e is opposite to each other, so therefore we will have a minus vector e1t. Alright, so same goes to the integration of for line from b to c. In this case is this part, and because of the direction of this line is corresponding to the normal component for this vector, and with the fact of this line is consists half of this line is exists in the medium 1 and the other half is exists in the medium 2. So basically the line integration for this line can be divided into two parts. Is equal to minus e1n, so vector normal vector for the e1 vector, and because of, as we can see here, so the direction of this vector line and the direction for the normal component for this vector is opposite to each other, so we have a negative e1n multiplied by the length of this line that exists in the medium 1. So we assume that this line is equal to delta H divided by 2. So that's why in this particular case the solution of the L is equal to delta H divided by 2. So same goes to the second part for this integration process. So we will have half of the line is exists in the medium 2. So therefore we will have the other half of this line integration is equal to minus vector e to n multiply with delta H divided by 2. So same to this part, so because of the direction for this line vector and the direction for the normal component for the e2 vector is opposite to each other, so therefore we will have the minus sign here. For the third part for the integration, which is integration line from c to d e dot dl, so we have this line. So because of the direction of this vector is corresponding to the direction for the tangential component of the e2 vector, so we will have the solution for the third part of this expression is equal to vector of e2t. So this one is the tangential component for the e2 vector multiplied by delta L, whereas this delta L is solution for the dl here, which is equal to the length of this line. So similar to the second part of this equation, so the last part of this equation, so we need to divide it into two parts. So first is from D to the middle point of this line, which is this line we consider is exists in a medium 2. Then we will have plus vector of e to n, so this one is the common normal component for the e2 vector multiplied by delta H divided by 2. And in this case, because of we can see that the direction of this line and the direction of the normal component for the e2 vector is the same, so therefore we will have plus sign here. And the same goes when we solve this second part of this equation. So the delta L here is equal to delta H divided by 2. And the last part of this fourth part of the equation, so we will have plus a vector of E1n. So this one is the normal component for the E1 vector multiplied by delta H divided by 2. Alright. If we take that the value for the delta H is near to 0, so that means this part of equation will be 0. Whenever part that involved with delta H value will become 0. So therefore, we will have the solution for the equation for the Maxwell equation that I just shown like just now is equal to this one, whereas 0 is equal to minus vector of E1t delta L plus vector of E2t multiplied with delta L. And if we solve this equation, then we will have the vector of E1t is equal to vector of E2t. Since we have expression that relate of electric flux density and electric field intensity as shown in this figure, and with the fact of the vector of D as well, we can derive it, or we can divide it into two component, which is normal and tangential component. So we can have the expression or the relationship between tangential component of D1 and the D2 as shown in this equation. So whereas the vector of D1t divided by epsilon 1, so this one is the value of electric flux that exists in the medium 1, is equal to vector of D2t divided by epsilon 2. So this one is represent the value of electrical flux that exists in the medium 2. So in order to solve the normal component, so we just solve the tangential component only. So in order to complete our analysis, so we need to see what is the solution for the normal component of that particular vector. So let's, based on the Gauss law, so we have this expression, whereas the closed integration for surface D vector D dot ds is equal to charge enclosed. So in order to use this equation, so let's build our Gaussian surface in a cylindrical shape like this shape. So we have three different surface here. So we have top surface. So the area for this surface is equal to delta S. So the unit vector for this area is equal to n1 cap, and this is our normal component for the vector of d1n. Same goes to the bottom surface. So we have the area for this surface is equal, it is the same as the delta S, as we just see just now. So we have d2n, which is represent the normal component for the d2 vector. So the direction of this vector is the same as the direction of electric field intensity, but in this particular case, the unit vector for this area is equal to n cap 2. So the height of this cylinder is equal to delta H, and we divide it equally between medium 1 and medium 2. So therefore, the height of this cylinder under medium 1 is equal to delta H divided by 2, and the height of the cylinder under medium 2 is equal to delta H divided by 2 as well. And by considering the charge in this area exists in the surface, so we will have the charge surface here is equal to rho s. Alright. First, because of the charge exists in a surface charge density, which is equal to rho s, so we can represent the value of charge by considering the density value is equal to this equation. And in order to solve the closed surface integration that represent in a Gauss law, so we should find the surface integration of the top surface plus with the surface integration in a bottom surface and as well as for the side surface. Alright, so same as what we did just now. So we assume that our delta H is near to 0, so that in this part of integration, so we will have the value for this part is equal to 0. So that means it left us with this expression. So whereas the closed surface integration vector d dot ds is equal to surface integration of top, so d1 vector multiplied by this is the unit vector for the area dot ds, so plus surface integration for the bottom, so the vector of d2, so this one is electric flux that exists in the medium 2, so dot with n cap 2, so this one is the unit vector for the area on the bottom surface dot ds. By assumption that, so this solution for ds is equal to delta s, and with the fact of the n1 cap is equal to minus n2 cap, then we will have the solution for this integration is equal to this expression, whereas n1 cap vector of d minus of vector of d2 dot delta of s. So this expression will result normal component for the vector of d. So therefore, so we will have d1n, so minus d2n multiplied by delta s. So in this case, because of previously we are performing a dot product, so in this case the value that we have here is represent the amplitude of the vector. At the same time, so the closed integration surface for ds is equal to this expression, whereas this is what we have been we have solved just now in terms of solution for the charge enclosed. Therefore, so we will have the solution for the Gauss law expression that we just performed just now is equal to d1n minus d2n is equal to rho s. If we consider this expression, whereas the vector of d is equal to epsilon multiplied by the vector of E, then we might have epsilon 1 E1n. So this one is the electric field that exists in the first medium minus epsilon 2 multiplied by E2n. So this one is the value of electric field that exists in the second medium is equal to rho s. So first, for summary of the boundary condition for other case, so you may refer to the table 4.3 in the book of Fundamental of Electromagnetics written by Fawaz T. Ulabi. Alright, in order to understand our topic, so let's look on this example. So let's consider one surface that resides on xy plane, and this surface is used as a boundary between the first and the second medium. For the first medium, it has relative electric permittivity is equal to 4, and the second medium having relative electrical permittivity epsilon r is equal to 3. So the electric field is travel from the medium 2 to the medium 1, and the vector of electric field intensity that exists in the second medium is represented by this vector, so vector of E2, and then the vector of E1 is represent the vector for electric field intensity that exists in the first medium. As usual, so this vector can be derived into two different components, which is its normal and a tangential component. And the theta 1, theta 2 is represent the angle between this vector and the y-axis. So we assume that on this particular surface, so there is no free charge exists. So we are given the expression that represent our E1 vector is equal to x cap 5 minus y cap 2 plus z cap 3. And then we need to find the expression for the vector of E2 and the angle, the value for the angle theta 1 and theta 2. Alright. As we have just now, so we will have the vector of E1 can be represent into its two components, which is the normal component and the tangential component. So the normal component is represented by this vector of E1n, and the tangential component is represented by the vector of E1t. By looking into this figure, so we can have that the vector of E1 in the normal component is equal to vector of E1 in the z cap direction. And in terms of tangential component for this vector is equal to the component of x cap and y cap that exists in the vector of E1. So therefore, the normal component for the vector E1 is equal to z cap 3, and the tangential component for the vector of E1 is equal to x cap 5 minus y cap 2. Since we have just now, so the vector of E1 tangential or E1t is equal to vector of E2t. Therefore, we can have expression for the vector E2t is equal to x cap 5 minus y cap 2. By assumption that there is no free charge at the surface as mentioned in the question just now, so we will have the value for the rho s is equal to 0 coulomb per meter square. So therefore, we will have the normal component for the D1 is equal to the normal component for the D2, vector of D2. And by assuming that, so we have relationship between D and vector of D and vector of E is equal to this expression, whereas vector of D is equal to epsilon multiplied by with the vector of E. Then we will have epsilon 1 multiplied by the vector of E1n. So this one is the normal component for the electric field for the vector of E1 is equal to epsilon 2 multiplied by the normal component for the electric field intensity that exists in the second medium. And because of we have expression that our epsilon is equal to epsilon r multiplied by epsilon naught. So this one is the relative permittivity. So this one is the air permittivity. So we can solve this one and we will have the vector of E2n. So this one is the normal component for the E2 vector is equal to epsilon r1. This one is relative permittivity for the medium 1 divided by epsilon r2. So this one is the relative permittivity for the medium 2 multiplied by the vector of E1n. If we replace this expression with the value that we have, then we will have the normal component for the vector of E2 is equal to z cap 4. So therefore, we have expression of vector of E2 is equal to vector of E to n, so this one is the normal component, plus with the vector of 2t, so this one is the tangential component for this vector, then we will have the expression that represent by this vector of E2 is equal to this expression. So whereas vector of E2 is equal to x cap 5 minus y cap 2 plus z cap 4. Alright, so in order to find the angle, so what we can do is just applying this concept. So whereas come from a dot product operation, okay, whereas so we have cos theta 1. So cos theta 1 is the angle that exists between the vector of E1 and the z-axis. So we will have cos theta 1 is equal to dot product between vector of E1 and the z cap, so divided by its amplitude. So by solving this operation, so we will have the theta 1 value is equal to 60.9 degree. Same goes for the theta 2. So we are using almost similar formula, but having different component. By solving this equation, then we will have the value for the theta 2 is equal to 53.4 degree. Alright, so in order to demonstrate your understanding towards the topic that we have been discussed, so please prove that the tangential component for both vector of E, so this one is the electric field intensity, and the vector of D, so this one is for the electric flux density, and conductor dielectric boundary condition is 0. So please submit your exercise by using your own handwriting. So please provide as well your name and the matrix number in your answer. Scan it and submit through ULearn. Alright, so that's all for now. Should you have any further question or feedback, so please submit it through ULearn. Alright, so good luck. Thank you very much.